Hello guys, Sir DV again here to continue our discussion on analysis of stresses. So today we will be formulating some equations on how to deal with equilibrium, no, of a body, a continuous body acted upon by a force, including the body forces, okay, and the traction forces. So we have here an irregular body defined by the region R here. Okay, so we have a region R upon which the boundary is described by the surface of this body. Okay, so this is a three-dimensional body on a right-handed coordinate system. No, so the permutation is a positive 1, 2, 3 permutation, y1, y2, y3 permutation. Okay, so it is on the counterclockwise direction. So you may actually change the direction of the axis, but it's no longer a right-handed system. And we all know that the right-handed system is the standard universal system that's being used by almost all softwares. Okay, so this body is now bounded by the surface of this region, and of course the domain upon which the boundaries are defined involves the volume. Okay, so here the boundary refers to the surface. Okay, while the domain of the representation of such body is actually the volume of the body. Okay, so this body is acted upon, of course, by what's this? This is the body force Fi, or simply the weight. Okay, the body force Fi or the weight Fi concentrated, of course, on the centroid of the differential volume that is being defined. And if we have a traction force or a traction vector, stress vector applied at the surface, at its differential surface defined by an area, let's say dA here. Okay, so this will constitute now a component upon which your normal, okay, the normal direction Ni defines your surface. Okay, so this is an irregular surface, therefore Ni may be oriented arbitrarily, not necessarily the same as that with your with the direction of your traction force. Okay, and if we consider the force equilibrium condition, so we are now deriving the equilibrium equation in terms of a summation of forces equals 0. So we know that summation of forces along y1, y2, and y3 are the forces involved here. So we have actually three directions here. Okay, y1, y2, and y3 directions. But again, since this is a vectorial or tensorial representation, we don't have to consider it one by one, but instead refer to it as on the terms of the subscript I, no? Where I here refers to the range in which your dimension, spatial dimension, is defined on the basis of y1, y2, and y3. And if we consider, we know that the forces simply involves your traction force, sigma I, multiplied by a differential surface area, okay, which is ds here. Okay, so ds here is actually your dA here, okay? So let's not use dA instead. So this is actually your ds, because your total surface area is considered S, then The attraction force, which is located at the point P, will be defined by the differential S upon which the orientation of shell surface is defined also by the normal vector and Ni reckoned from that point. Okay, so that's how this system of a continuous body is described based on continuum mechanics. And we consider now again the traction force here plus the body force. Okay, the traction force plus the body force is equal to 0. Okay, so this is a static equilibrium condition. In a dynamic equilibrium condition, what will change here is an addition of what? Of an inertia force. Here we only consider the gravity in terms of the density defined on your rho Fi value. Okay, so this is now the general equation in continuum mechanics, considering static equilibrium. And by substituting the definition of a traction vector sigma I in terms of a nj sigma ji or sigma ji nj, then we can now make use of equation 2.6.1 as your basis for your force equilibrium equation. But before we can continue, let us try to understand what is the theorem of divergence in terms of Gauss proposal or Gauss proposition. So remember that we have two domains, or sorry, not two domains, but two different dimensions or units. We are adding an area with a volume, so we cannot directly add an area domain with a volume domain, a boundary with a volume. Okay, so that is now the purpose of introducing to you the Gauss divergence theorem, for you to be able to relate the volume integral or the domain integral to a surface integral, or what you call the boundary integral, or vice versa. So there's a relationship between the boundary and the domain. Just like thinking about how big will be your volume when your surface is big. Okay? Let's say the surface area of a certain body will depend on the actual volume of the body. If you have a bigger volume, you expect a bigger area. So at a certain aspect of such relationship, we can define a theorem known as the Gauss divergence to relate these two dimensions for us to come up with a simpler equation later. And in terms of tensorial expression, this is now your Gauss divergence relationship, relating the domain with the boundary. So this is now the boundary, ds, and this is the domain or the volume, dv. Okay, the boundary constitute the limits upon which the domain will be bounded or limited to. You cannot exceed within the limits of the boundary, or else you are being inconsistent. Just like the limits of your property, you cannot exceed on the limits of your property. If your boundary is defined in terms of your perimeter boundaries, then the area, the domain of your area, the lot area will only depend on that limit. So this is what the Gauss divergence theorem is all about. Okay, the integral of your tensorial quantity multiplied by uh, the normal, okay, the normal vector uh, described in the boundary is equivalent to the integral of the partial derivative of your tensorial quantity described in the volume. Okay, so you are now relating a derivative with the derivative of the tensor with the tensor itself, but there's an additional multiplication, a dot product on the normal vector defined in terms of the surface area of reference, ds. Okay, take note that the dy is simply the partial derivative, also known as your del operator. So the del operator is written in terms of an inverted triangle like that. Okay, so applying the theorem on the first term of equation 2.6.1, then we take note that the stress, the tensorial quantity is simply the stress tensor in question. So this is the tensorial quantity T that we are referring on the divergence theorem. Okay, so this is T dot N ds is equal to the integral of d dy T dv. Okay, so this right hand side now may be written in terms of volumes. Okay, so this is now the equivalent. So this is now your equivalent there, which is simply equal to another. So this is just another form of, because in other references you might be seeing a ji comma j, which simply refers to the partial derivative or the derivative of sigma ji with respect to j or yj. Okay, so ji refers to the tensorial subscript, while j here refers to uh, the position vector. Okay, when you say position vector, that is the xyz. Okay, position vector are simply xyz, x1, x2, x3, etc. No, so you can have y1, y2, y3, z1, z2, z3, or simply 1, 2, 3. No, so hence this equation 2.61, courtesy of Gauss divergence theorem, becomes this one. Okay, so this I just place it there, and then plus the body force. So this is now your uh, uh, the traction force plus body force is equal to 0. And remove the integral sign by removing the differential volume. Cancelling them out will let you remove the integration procedure. Hence, sigma ji comma j plus rho fi will now be equal to 0. And this, again, I'd just like to take note that this is simply equal to the partial derivative of sigma ji with respect to xj. Okay, xj is simply xyz, x1, x2, x3, or y1, y2, y3. Or you can take the derivative, the full partial derivative. Okay, so this is just a shortcut. Again, what's the purpose of indicial notation? To cut off all the unnecessary symbols that we can cut off in order to make it more compact but precise. Okay, so if I ask you now what is the force equilibrium equation in continuum mechanics in terms of static equilibrium, so this is now your answer. Okay, so in the next presentation, I will be discussing to you the moment equilibrium equation, which is almost the same in terms of the derivation presented here, but a little more involved and stringent. So thank you for listening, and I'll see you on the next video.